Okay, so the last thing I want to do as part of the uh, thermal analysis is that we're trying to figure out, right, if we're in the ballpark of meeting our programmatic requirement to comply with local law 97. So to do that, we we need a number of in terms of carbon footprint, and we'll get to that, but I'm not going to worry about that right now. One thing we're going to assume is that no matter what it is that we're whatever it is that whatever level of carbon emission footprint we get to with our building design, it's going to be augmented by adding energy production. So the equation is you have whatever energy you're using in the building, operational energy, and then if you produce energy on site in a renewable way that's has a lower carbon footprint, like photovoltaics, then you get credit for that energy, and that you subtract that from whatever your site EUI is. So we're going to use this Grasshopper workflow. This is a preset thing that I'm going to supply when we do the course. But we'll get into Grasshopper in more detail as we move forward. But let me just tell you quickly how this works. Grasshopper, if you haven't used it, it's just a visual coding language. So each of these little boxes has got code in it, and so they're just think of it as like an equation basically, more and less complicated, but they allow us to use to create code really quickly from preset packages. And so, for example, Climate Studio has a ton of Grasshopper workflows. They have, I'll get into that later. But anyway, this is really simple. We're going to bring in some PV panels here. We're going to identify a surface area that is going to be our PV panel area. We could actually design panels and do a bunch of other stuff, but we're going to keep it simple, just to get some real basic idea and just to run through the workflow. So we're going to define a surface area in Rhino, and that's so all we're doing with Grasshopper is just accessing Rhino geometry and either changing it or analyzing it based on some other inputs. Then our PV panel, taking that input geometry, it's going to have a certain efficiency. So we're going to say 0.2. That means 20% of the surface is going to produce electricity. That's a pretty normal, but high on the higher end. Maybe now it's normal solar efficiency. Then we're going to say that 80% of the area is also producing. So of the surface we define. So I'm just going to define the surface of the roof and say that 80% of that would be PV panels. Is that accurate? I don't know, but I mean that seems reasonable, and we're just playing around. Then there's a component that does the actual calculation, and then this is all outputs over here that are also components that are easy to access. I ran it last time. I don't know what this was, so let's go do it. So I'm going to go into Climate Studio, and I'm sorry, Rhino. Let's see if maybe I don't have in this model. Oh yeah, I did. Okay, so I just identified the roof itself. You can see that's the surface. It's just the surface area, that one B-rep or polysurface. And now I'm going to come over here into Grasshopper and set one B-rep, and then that's all we're doing. And then I'm going to run it. And now we see we're producing with that, with our basic really lame analysis, 26 kilobtu's per square foot per year. And if we go back and look at our site EUI, we're at 15 with this, all the crazy stuff we did. But we even just with the basic 90.1, where was that? With curtain wall, we were at 35. So we're still, that's now we're, but this would show you why this is important, this kind of performance modeling too. So with the basic high performance building, we're at 35 site EUI, 35 kilobtu per square foot. And we were estimating that we could maybe able to produce 26 kilobtu per square foot. So we'd have 9 per square foot. We'd have to figure out if that was going to meet local 97. But if we do some more optimization, we can get it down to 15, and we're actually carbon negative here, right? We're producing more power than we need on site, so we know that's going to meet the standard. Um, and we could also, or we could say, well, what happens if we actually use this whole, um, you know, we're going to say now that we're going to, instead of using this overhang here, we're going to bring it up on the roof and then use that as our roof surface. So that means we're going to have more area for PV. If I then bring that in, and again, this is just silly, not silly, but this is just, we're just messing around. We're not saying it's accurate, but now I went up to 33 from 26 by making that simple change. So, we can learn a lot really quickly. That's what I'm saying. And this is going to be the first level of LL97 compliance that we're going to do. And you can see that you could pretty quickly, we're in a climate that has a lot to do with how much energy we can produce. We can pretty quickly determine some estimate of what we think the square footage of our roof's going to be. And then we could, even if we just do it abstractly, we just, create I can create a surface over here. Oops, sorry. And bring that in to this. So it doesn't have to be on the building. It's just now we're in the climate. See, if I can run that, it runs really fast. So this is a very useful simulation that we can do quickly. It's the first thing we'll use in Grasshopper. So that's really the only other thing we need to know then really is, in terms of this basic thing we're doing in this class, is what the local law 97 requirements would be. I've basically made a decision on that, but I'm not going to worry about that right now. It's not important to you guys. Just this balance is kind of fun, this little game to play where you try to get your PV below your site EUI. All right. I hope that this is enough and not too much to get you guys sort of going on the modeling and seeing what you think, and we can talk about it. All right. Talk to you soon.